Okay, everybody. So last time, let's remember where we are. We are trying to understand the scheduling part of the threads and the processes. How do we schedule the processes and the threads? We are looking at that topic. We talked about it. We made our definitions, and we said that. Okay, remember. The states of a process that is runnable. Why everybody is so late? Are you making your plans? What? What? Yeah, so take the train one before, okay? So it is supposed to be here what? At what time? 10:35?
3 minutes ago.
What?
3 minutes ago.
10:30, 10:27? So you are already making your plans to be late for the class. Is that what you are doing? Because nobody is going to work faster than 3 minutes from station to here, right? So please come 15 minutes early. Okay, so scheduling is something that needs to be done. It is part of the core of the operating system, kernel of the operating system, and it is a decision of which process among all the ready processes, which process should run next, which process should use the CPU next. That's what the scheduling is. And we talked about that it depends on your environment, whether it's a batch environment or the interactive environment or a real-time environment. We talked about those, and we said that scheduling most of the time, scheduling would have been easy if the processes behaved the same way. Okay, if all the processes are doing the same thing, similar stuff, they are behaving the same way, and we can get away with very simple scheduling algorithms, but they don't. Some of the processes behave this way. They take the CPU and they use it a lot, okay? And some of them are designed this way. They take the CPU, they do very little, and they just immediately block, and they make a system call. It is not because these processes are designed in a bad way. It is not because their design decisions are bad. It is their nature, right? This is a CPU-intensive process. It needs to CPU a lot of the times. But this one needs to do lots of user interaction. User interaction means lots of system calls. Okay, tell the user this is going on. Get some data from the user and etc. So lots of short CPU bursts and lots of blocking. And this one doesn't require that much blocking. So it is not the fault of this process that it needs to do lots of I/O. So I shouldn't penalize this process because it is blocked most of the time. So if I give if I give the same priority for these two processes, in terms of CPU usage time, I know that this is going to use the CPU more, so it's not going to be fair between these. So what I'm trying to say is that the nature of the design principles of the processes are different. So their behavior of using the CPU and blocking is different. So I need to come up with some smart ways of scheduling these kind of processes. Okay, so we talked about those, and we talked about when to make the scheduling decisions. We talked about preemptive schedulers and non-preemptive schedulers. Remember, for the preemptive schedulers, you definitely need, okay, clock hardware, okay? So clock hardware is the one that creates an interrupt every, let's say, 40 milliseconds, okay, maybe 50 times a second, etc. And since when the interrupt happens, the operating system has to handle it. That's why we say that operating system will take care of will take the CPU, and it will do the scheduling decision while it takes it. Okay, so that's the small reminder again for the preemptive, non-preemptive schedulers. And most of the, as I said before, most of the modern operating systems that we use for the desktop operating systems, of course, they are all preemptive. For the especially for the interactive systems, it is very important. So let's look at these scheduling algorithms. Okay, so as I said before, scheduling depends on what kind of environment you live in. Okay, if you are in a batch environment or interactive environment or the real-time environment, in the batch environments, you know that you have a very expensive computer like a mainframe, like a server, and this server is doing one thing, and when it finishes up with the first thing, then it does the second thing, and the third thing, etc. For example, it is printing. For example, it is calculating the invoices of my cell phone customers. I have 10 million cell phone customers, and at the end of the month, I need to calculate their bills. And calculating the bill means that I need to list all the phone calls that they made and multiply it with some number depending on the time and etc. and etc. Okay, so for example, I am doing this. After doing that, I am going to calculate the bills for an electric company and etc. I don't know. I mean, so it's a very repetitive process. It will take maybe a few hours, each of these batch jobs, but I don't have any interactivity, right? So I don't need to talk to any users. I don't need to do any interactive stuff. So most of the time, it is CPU intensive stuff. Batch processing stuff, so responsiveness is important. So maybe for these kind of operating systems, maybe I don't need the preemption, because, as I said before, preemption is important if there is interactivity. Okay, so that's one thing for the batch systems. For the batch systems, the important thing is the CPU and the system utilization. Okay, is my CPU idle? If it is staying idle, it's an expensive computer. I shouldn't do that. Okay. So that's the motivation. For the interactive systems, human is the number one priority. I shouldn't keep my human user idle. When he or she says do something, I should immediately either show some kind of a response or do it immediately. So I should be interactive. That's why we say that preemption is important. So I cannot let a process take the CPU and use it for 10 seconds without giving it back, and after that I get the CPU, and again that process takes the CPU for another 10 seconds. I can't do that. So that's why preemption is important, and I should stay interactive. Okay, and the real-time systems. Remember, for the real-time systems, when the operating system says that I am going to do this, it should give me a guarantee that it's going to be done in like 50 milliseconds. An operating system should guarantee it. Okay, so also any process taking the CPU, you are given only a small amount of time. Maybe I shouldn't say small, some fixed amount of time. It says that whatever you are going to do, you are going to do it in this amount of time. And if you are not done, then I will take the CPU from you. So often they are not preemptive, because by the nature of these kind of operating systems, I mean this is already like, okay, a second of CPU time, I say that, okay, this time will belong to process A, process B, process D, C, D, and this time will be empty. I am keeping it empty in case something happens. Okay, and I'm going to do this over and over again for each second. Of course, between these, operating system takes over. The operating system is doing something that too. So the preemption is not, for these kind of systems, we don't talk about preemption because every process has its own time slot already. Okay, so these are some of the categories of the scheduling algorithm. So I am going to do this. I am going to look at the scheduling algorithms for the batch systems, interactive systems, and the real-time systems. Let's start with the batch systems. Remember, with the batch systems, you are supposed to do one task. After the task ends, you do another task. After the task ends, you do another task. So what is the scheduling decision then? At the beginning, who is going to start first? Okay, that's kind of important. So that will be the idea. Doesn't matter what kind of operating system you are dealing with. Okay, these three things will be important. Fairness. Okay, you need to be fair between the processes. Give each process its share of the CPU. Okay, so because you have some kind of a policy doesn't mean that one of the processes is starving while the others are having the CPU. So you need to be fair, of course, depending on your system policy. Okay, if your policy says that you are going to favor these kind of processes, then that's another topic. The second rule is policy and enforcement. When you say that in my operating system, high priority tasks will be given more priority, of course, than the low priority task. That's kind of obvious. If this is your policy, then you should enforce it. Okay? And you should not have any ways of subverting, okay, this policy rule. Remember the priority inversion problems? So be careful about those kind of problems, and we will talk about this priority inversion problem in a few minutes. So if you say that this is my policy of scheduling, then follow that policy. Don't let any kind of problems violate the rules of your policy. You might say that, well, it's a policy. What is wrong with violating? But once you start violating those kind of policies, you will have contradiction in your system. And those kind of contradictions will create some nasty problems down the way. And I'm going to give you one serious problem, historical problem, that kept lots of people wondering what's going on, and it was going to be a disaster. At the last minute, they solved it. And the balance is usually this is good for the most valid for the mainframe computers. Keep all parts of the system busy. Okay, you might say that. Well, my CPU is busy. What should I do? Maybe you should do the tasks that need the hard drive first, so that you can keep the hard drive, then let the other tasks that need the CPU. So you are keeping your hard drives and the CPUs all busy. So you are using your whole system more efficiently. So these three things, we will talk about them from time to time when we talk about these specific batch, interactive, and real-time systems. Okay, so let's look at this batch systems first. Our goals here again, system efficiency. That's the most important thing. CPU utilization. Keep the CPU 100% if possible busy. But while I am doing this, so what is the difference between, let's say I have three tasks, A, B, C. If I run them in this order, my CPU is 100%, okay, busy. If I do this, B, C, A, again my CPU is 100% busy. So it looks like, I mean, assuming that I don't have any blocking and that kind of stuff, doesn't matter really. So what is the decision? What am I basing my decision on in this case? I mean, what is the difference between ABC and BCA? In this case, they made these two definitions, throughput and turnaround time. Okay, throughput is this: maximize jobs per hour. Are you going to do this in 6 hours or 8 hours or 10 hours? Are you going to do this again 6 hours, 8 hours, and 10 hours? It looks like, I mean, what is the difference? I mean, I am going to, at the end, I am going to do all of them, and whatever the total time required for ABC, if you add them up, it will be my throughput. You might say it that way. How about this turnaround time? Return jobs quickly, often want to finish. Okay, so that's the turnaround time. Turnaround time is what is the average waiting time for each job? Well, in this case, maybe this might be a good heuristic to make it. Well, it's not a heuristic, it's a very good rule actually. If you like to keep your turnaround time smaller, shorter, then this is the rule. You want to finish short jobs very quickly, okay? If A is going to take, let's say, 10 minutes, this one is 2, this one is 1. So this rule says that do C first, so that it will be done in just 1 minute. Then B, okay, if I do C first, okay, it will be 1 minute for this job. Then do B. For B, 2 minutes will be for B, but 1 minute is going to wait for C. It will be 3 minutes. And A will be 13 minutes. If I do it in this order, C, B, and A. So the total is going to be 17 minutes. Okay? So 17 minutes over 3 is around 5 point something. How about this order, A, B, C? If I do it A, B, C, A is going to take 10 minutes. Okay. B is going to take 10 minutes for A time, and this is 30 minutes, and C is going to take 14. That will be 37. Okay. So 37 over 3 is definitely longer than 17 over 3. So for the throughput time, okay, the rule is often you want to finish short jobs very quickly, and we are going to look at this, okay? So you might say that the CPU utilization is the same, but if you like to maximize these kind of numbers, okay, what is your throughput time? What is your turnaround time? Then these will be the calculations, and we will see some examples of this in a few minutes again. Again, for the interactive processes, response time is our only. If your system needs to be interactive, whatever the cost, okay? Well, I mean, my cell phone needs to be interactive, but battery management is the other main concern, right? So I need to be balanced between the battery management and the interaction. But maybe for this one, for my desktops, maybe interaction is the #1 priority, especially for the laptops, right? Maybe for the desktop, you can do some CPU intensive job. For the laptops, nobody is supposed to do lots of GPU sensitive, CPU sensitive stuff. Maybe for the laptops, battery is kind of important, but I can always use the power, okay, wall power. So interactivity is the most important. So respond quickly to user requests. Okay, that's the rule. So what does the quickly mean? Okay, I mean, what do I mean by quickly responding to user requests? That's kind of human psychology comes into play. Human psychology. Humans behave very differently. I mean, they are very different creatures than the computers. They have a sense of cheap and expensive requests. For example, mouse click. When you say that I like to highlight this word, when I click on this thing, just a simple painting, right? I expect that it is to be done very, very quickly. It's a very simple thing, okay? That's my expectation as a human being. On the other hand, if I say that move this directory, which has 5 gigabytes of data, to another place on my hard drive, I kind of expect that, well, 5 gigabytes is lots of space. Well, it might take a few minutes maybe, okay? So what I'm trying to say is that what the humans think as cheap may not be cheap for the computers. What they think is expensive, it may not be expensive for the computers. So when you are designing your operating systems that are supposed to be interactive, they have to take the human psychology into play. Okay, into play. Humans hate it when I click a button and nothing happens. Did I click it right? I don't know. Did the system take it? I don't know. Is the system working or it is not doing anything? I don't know. People don't like this kind of a behavior. So as soon as I click a button, I do something, I need to see some kind of a response on the screen. That's how we work. Okay? When I ask a question, to somebody, even if I don't know that person, I expect a response. Yeah, right. I mean, if I ask a person a question, where can I go to the? How can I go to the library? And if that person doesn't make any response, doesn't say, I don't know, this way, or even a rude gesture, you kind of feel weird. I mean, what's going on? I'm asking a question, is he deaf? Didn't hear me? And that kind of stuff. It makes it confusing. So you expect the same behavior from the computers, and operating system is at the center of it. Try to meet the expected cheap and expensive requirements of a person, and sometimes this may not be possible. And remember the last time when I say I am trying to just make this zoom in it and zoom out, and it didn't respond, and I was kind of frustrated. For me, it's a cheap thing; it is not doing it. But I am okay when I try to load a new file. It is okay for me to wait like 10 seconds, 20 seconds. I get used to it because sometimes opening a file takes some time. That's what we are saying, human psychology. Okay, and for the real-time systems, we talk about the meeting the deadlines. You either do this in given amount of time, or your system is junk, just a piece of junk. Okay, I don't need such a system. Okay, meet the deadlines, or this whole computer is a useless computer. So it has to be predictable. Okay, I need to know as an operating system, custom operating system user, I need to know when my request will finish. Okay, for Windows or for Linux or for any kind of operating system, non-real-time operating system, when you say move this file from this location to this location, most of the time it is done instantly. Sometimes it might take a few minutes. Okay, we don't know what's going on, especially when the mechanical hard drives are involved. Mechanical hard drives have this behavior of calibrating their heads from time to time. When they decided that the heads are out of calibration and they need to calibrate it, it might take sometimes 20 seconds to recalibrate those heads. So for a task that usually requires 100 milliseconds, sometimes it's going to take 20 seconds. Okay? And Windows doesn't guarantee that there is an upper limit for this kind of behavior. Okay? For the real-time systems, they say that no, it is going to be 20 milliseconds at most. That's it. That they guarantee it. So, well, if they use the mechanical hard drives, how do they can give such a guarantee then? I mean, if the mechanical hard drives behave this way, sometimes they are very, very slow to respond. How do you make such a guarantee in a real-time system that uses the hard drive? Any ideas?
You make it much more than it usually is on average.
Oh, you are saying that your time slot is 20 seconds. No. Well, even 20 seconds sometimes is not enough. No. And by the way, 20 seconds is not realistic. It's not realistic time slot for a real-time system. We are talking about 100 milliseconds and that kind of stuff. No. Yes?
Using two disks at the same time.
Using, well, I mean, that might make it less likely to wait for 20 seconds, but I mean, once in a while, once in a year, it will happen. The solution is very simple, actually. Real-time systems, they don't use hard drives. That's it. Because I mean, in a system like that, that depends on the hard drive, they don't use it. Well, what do they use? They use maybe SSDs. Even SSDs might create these kind of problems. Well, real-time systems, sometimes they are very, very limited systems. Okay, they don't save data. Okay, they say that we don't save data. You initialize me, and I work as long as I have the power. Okay, as long as I have the power, I work. And when the when the power goes off and I die, and that's it. How do you save your data? Well, my task is to keep this nuclear power plant alive. I will guarantee that your temperature will never go above this much. I will guarantee that my electric output will be at least this much, and that will be it. I am not going to be interactive. I am not going to be taking your backup your data. For those kind of things, you use your regular operating system. Okay, so they are very, very limited systems. The reason is their main purpose is meeting the deadlines, not the CPU utilization, not the interactivity, but the meeting the deadlines and predictability. Okay, so let's go back to batch schedulers and let's talk about these batch schedulers. We will talk about 3 scheduling algorithms. As always, we will start from the simplest one, first come, first served. Okay, so the first come, first served is, as the name implies, if I have A, B, C, D, E, these are my processes, and they come to my batch system. And we say that I will start with A, then B, then C, then D, then E. That will be the order of the batch systems. And this is as simple as possible. It will keep my CPU as busy as possible. But again, if I do that, my throughput time and turnaround time might suffer, and we will talk about that. Okay. So run the first process on the run queue. Okay. When the running process blocks, you may choose to have a multi-task operating system. The first process on the queue is run next, and we never preempt based on timer. Why do you think that we are not doing any preemption in this case? Batch processing operating systems, they don't do preemption. Even they have a timer hardware. Okay, but these are expensive computers, right? I mean, having a timer hardware is not a big issue. They can give the money, but we never preempt based on the timer. Why don't we have the preemption on the batch systems? It is irrelevant. You might say that there is no interactivity, right? Well, that's okay. I mean, what is wrong with having a timer and switching from one process to another process?
Context switches, interactivity is not like the main purpose of it.
Yeah, well, that's what I said. I mean, even if I don't need interactivity, what is the problem with switching from one process to another process every 100 milliseconds? Yes? Context switching. Well, I mean, how many times I'm going to ask the same question, and how many times you are not going to tell me it is context switch? In operating systems, if you don't know the answer to your question, to my question, the answer is context switching. Okay, just write context switching there. Okay, and I will understand what you mean. It is. I mean, why do I get this hit of the context switching? Context switching is expensive. Okay, it is expensive. It is not saving your registers. It is invalidating your cache. Megabytes of data is going to go, okay? And it will take lots of time to load them back, okay? So it seems simple, just like waiting in the line. And not a very fair, okay? Not a very fair scheduling algorithm. Why? Because, I mean, first come, first serve means that whoever comes first by coincidence, they will get the CPU, and if they are CPU CPU intensive jobs, then they will keep the CPU. So they are not very fair. I mean, remember one of the concerns about the scheduling is the being fair. But in this case, as I said, I'm in a batch environment. I'm talking about CPU utilization. Maybe sometimes just don't be fair to some of the processes, and that will solve it. So the other thing is that, well, this is too primitive, first come, first serve. Let's do this shortest first. That's the idea, okay? Let's say I have 1, 2, 3, 4 jobs, okay? I know that A is going to take 8 minutes, 4 minutes, 4 minutes, and 4 minutes. How do I know that 8 is going to take 8 minutes? A is going to take 8 minutes. How do I know that? Well, remember, these are batch systems. Yes?
We can count the number of instructions.
A number of instructions hardly tell you how long it's going to take. I mean, if you are in a very large loop, just 3 lines of code might take lots of time. I mean, don't count the number of instructions, but count the running number of instructions, maybe. But how are you going to do it without running it first? Well, these are batch systems. What did I say? What kind of examples did I give you? Every month, once a month, I calculate my payment amounts of each of my employees, right? I did it last month, okay? Last month it took me 8 minutes. This month I didn't hire lots of new people. I didn't fire lots of new people, so it's going to take 8 minutes. Okay, those are my guesses. Since these are batch jobs, I know how many seconds, how many minutes they are going to take. Okay, so let's say from my experience, I know how long they are going to take, because I am doing almost the same thing over and over again every month, every day, every night. I don't know. Okay, so I know 8, 4, 4, 4. So let's do the same thing. So that will be the formula, right? If I do this, A, B, C, D, that will be my turnaround time. 4A times 3B plus 2D plus D over 4. What is this 4A? Why is this 4A? 4A is because, well, obviously, let's before that, if this is my turnaround time, you want D to be the largest number, A to be the smallest number, right? I mean, A should be the short one. That's why we say that with the shortest first algorithm, my turnaround time theoretically should be the minimum. But where does this 4A come from? Did you understand it? Yes?
Actually, this statement is the total number of total time of the all processes.
Yeah.
So every A is the time of the other processes. Comes from the other processes.
Exactly. For D to run, I have to run A first, then B, then C, right? So for D, okay, I will have to wait 8 plus 4 plus 4, so it is like 16, 20 minutes for D to finish. For C to finish, it will be A plus B plus C. I have to wait 16 minutes. For this one, it is 12, and for this one, 8. So my turnaround time, my expected turnaround time for this system is going to be 8, okay? It's going to be, for D, it's going to be 20 plus 16 plus 12 plus 8. Okay, it's going to be that way. So every time I am adding it, that will be A always will be added to the running times of D, C, B. That's why you do it this way. If I do it this way, okay, A will have to wait only this much. B, C will have to wait only this one. So shortest one first will increase your shortest time first will increase your turnaround, will make it better for your turnaround time, it will be smaller. Okay, so it is probably optimal turnaround time. Again, non-preemptive, this one, shortest first. And what did we say? We don't use the preemption, but it looks like we are going to talk about preemption in a few minutes for the batch systems. That's because in this case we assume that, and this rarely happens, we assume that, and for this one too, first come first serve too, okay, we assume that all these jobs are available when we start scheduling, but this doesn't happen, right? When you come to work in the morning at 8 o'clock and you have seen that there are 4 jobs available and you start running, this doesn't happen in the computer world. Things are dynamic, okay? First you have a job. While you are running a job, another job comes in. While you are running again, another job comes in, okay? So the situation is dynamic. Let's say I am running A. While I am running A, I got 2 jobs, B and C. Then I got another job, D. Well, I started running A. I am running it. And since it is the longest one among all the others, what am I gonna do? Since my system is not preemptive, I will keep running A even though I know that my turnaround time is going to get a hit. So they solve this problem by coming up with a new algorithm. They say that, okay, why don't we make this algorithm shortest remaining time next? Okay, so this is the preemptive variant of first come first served. Okay, so but again it is doing the shortest time too. What am I gonna do? Let's look at this example. Let's say I have 1, 2, this is A, B, C, D, and E. But I know that A and B came at time 0. This one, and this one, okay, came at time 1. Okay, while I am running, so the shortest A and B is available at time 0. So shortest first selects A. While I am running A, okay, nothing happened. I am running it. Then I started running B, okay, because the B is available now. At time 3, so let's do this. So for 2 minutes I run A, then I started running B, then C, D, and E came. So it looks like the remaining time for B is 3 minutes, but if I switch to C, D, and E, okay, then I can finish them before B can be finished, and later I am going to do for the last 3 minutes of B. Okay, so that's what I am doing here. I am doing the shortest remaining time next. So that requires me to have a preemptive operating system. That preemptive operating system, every time when the interrupt happens, I am checking how long do I need to use the CPU for this process, and dynamically it changes the picture if I have a new process coming in. Okay, so optimality requires simultaneous availability, that optimality, but if I don't have that simultaneously, then I am going to change this stuff. Okay, so if I keep doing this A, B, C, D, E, average wait time is 4.6 minutes. I said minutes, but the book says seconds. But if I do this B, C, D, E, and A, then it's going to be, okay, then it's going to be 4.4. Okay, good. So that's the shortest remaining time next. Preemptive variant of FCFS. Of course, we still need to know the run times in advance, but for the batch systems, it's kind of, I can find it, I can know it. Okay, when a new job arrives, its total time is compared to the current remaining times. and it helps the short jobs get good service, but it has this problem of, can somebody explain this to me? This is a problem. Maybe I should make it red. So red is a problem. May have a problem with infinite overtaking, or we have a nicer term for this kind of a problem. We have a nicer term. It's called what? Let's explain this first. What is this problem? Yes?
There's always new tasks coming short.
Yeah.
Less of time.
Exactly. We have-
task.
We have one unlucky long process. It gets being pushed back all the time because there are lots of short processes coming in. Okay? So that process is going to be pushed back and all the time. Infinitely will be overtaken. And that process will never get a chance to use the CPU with this kind of an approach. Okay? That's called starvation actually. I taught this. Starvation. It's açlık, kıtlık, whatever. So when starvation happens, actually the resources are available. I mean, in the modern world today, there are lots of societies with lots of food to consume, but like one billion of this world is living under the conditions of not having enough food. Right? They are starving, while the other part of the world is kind of obese, right? So kind of the same thing. One of the processes is not using the CPU, but all the other short processes are getting whatever they want. Okay, they don't care about the other unlucky process, that's the starvation, and we don't like the starvation stuff. Remember, one of our goals of the operating system scheduling, task scheduling, is to have a fair system. Okay. So don't let these kind of things happen. Maybe when you do the shortest remaining time next, maybe you should consider how long did you wait in the waiting queue kind of a condition too. Okay. Shortest remaining time, also your wait time. If your wait time is too long, maybe I'm going to take you. Okay. Good. So I think in banks, in Turkish banks, when you go there and you take a number, they give priority to the wealthy customers first, I guess. So if there are 5 people waiting and if 2 of them are wealthy, they take it. 3 people, they make them wait longer. But if there are many wealthy people are coming in, I think from time to time they take one poor retired customer, and etc. They do it that way, right? So anyway, I don't know, whatever they do, they always make me wait. Whatever algorithm they have, I don't know, I just wait there for some reason. Okay, good. Oh, okay. I think it is. Let's look at these numbers a little bit. These are kind of, yeah, I mean, when we talk about the seconds and the milliseconds, microseconds, the nanoseconds, and etc. Let's look at some relevant stuff. Remember, these are, okay, L1 cache reference. When you read a value from L1 cache, it takes 0.5 nanoseconds, very, very small amount of time. Okay. L2 is going to take 14 times more, 7 nanoseconds. Okay. So that's going to be a lot of expensive stuff, and we are not talking about the memory, right? We are talking about the cache. So it is very important to keep stuff in your L1 cache, but L1 cache is not a very large place because of the principle of the locality. Okay, and if you design your algorithm, write your code according to your cache sizes, you may have very efficient code. But if the context switch happens, all the data in your L1 cache is going to go away. All the data in your L2 cache is going to go away. And now you will have to drop down to 100 nanoseconds, which is a memory reference. So we are talking about, for each data reference, we are talking about 200 times more time. So that's what we are talking about. Context switching is expensive. It is not because you have to save data. Well, that's expensive too, but the more expensive part comes from your data invalidation of your cache. Our professional software that we use today, they are optimized for using the cache. Okay, if I had a single process and it is using the CPU and the memory, it is optimized for that computer, yeah, because it knows the structure. The compilers are very, very smart, very, very advanced. But when the context switch happens, I don't know where am I going to. I mean, I cannot predict that behavior, what the other process is. That's why we try to avoid the. That's why we try to avoid the context switching as much as possible. It's because of the difference between these two numbers. 100 nanoseconds per memory reference versus 0.5 nanoseconds. Okay, and yet we didn't talk about the memory issues. Remember, I can't fit everything in my memory, and I'm not talking about the cache anymore. I can't fit everything in my memory, and if I switch from my process to another process, that process's data and the code may not be in my memory. It might be on my hard disk or SSD. Well, in that case, we will talk about getting data from the hard disk. And do you guys see? Okay, SSD random read. Okay, from nanoseconds to microseconds. Okay, 1,000 times more time. Okay, 1,000 times longer, because we are now talking about the microseconds now. Okay, because and by the way, this is an SSD. This is not a mechanical hard drive. Okay, mechanical hard drive. So context switch is that expensive. Okay, 1,000 times more expensive than keep using the same process. That's why we don't like context switching much. But without the context switching, there is no multitasking. Without multitasking, no time sharing, and without multitasking, there is no modern computer. We have to keep all these in our heads when we are designing new operating system. Okay, any questions up to now? Good. Did everybody sign this attendance sheet? Let me kind of check if the signatures are lining up. Is Muhammed Bedir here? Muhammed. Who is Burak Ceylan? Burak Ceylan? And who's Faruk Ceylan? You are brothers?
Yes.
You are twins?
Yes.
Really? We have two sets of twins in this department? Okay. Good. And your signatures are the same. Okay, good. Okay, let's say 10 minutes of break. 11:35.
Seri var ya, onun videolarını izliyoruz. Orada kafa işte bir reis var yani. Süre sistemi burada. Yani nasıl bir şey olacak bilmiyorum.
Evet, davranış vermeye çalışıyoruz.
İletişim sağlayacak. Şey, kamera olarak ekranı paylaşıyor. Evet. Hiçbir saçma yani. OBS kullandığı için.
Saat ne varsa sol tıklayınca ön beyaz. Sonra burada yerine koyunca şuradan alıyor. İkisi aldı.
Ödevden sonra zaten şeyler başlıyor. Vizeler başlıyor. Evet. 11'inde.
Sürekli 30'luk loop şeklinde.
Buraya bundan sonra sonraki günde database var.
Database vizesi mi var ya?
Yarın değil. Bu dersin vizesinden sonraki gün.
Ha.
Bizi pazartesi.
Abi olmaz ya.
Çantamı göreceğiniz.
İşte daha bir şey çalışalım.
Ne yapıyor?
Yanında biri var mı?
Bir boşluktan sonra var.
Çanta vardı bir tane.
Boşluk sonra var hocam.
Proje nasıl gidiyor? Bir şeyler araştırdım.
Toplantıda, geçen hafta toplantıda şey yapmadım dedim. Okey.
Anlaca şey diyor böyle, her hafta bir şey yapmak zorundasın.
Evet.
Bir de şey var, sitesinde işte, yukarıya yazmış yok, son haftalarda yapacaksanız almayın.
Aynen.
Diğer proseslerde üst üste binerse faylı
Ya veri kümesini aldım, veri kümesini daha işleyemedim.
Ben veri kümesi tam bulamıyorum.
Benim belliydi neyi kullanacağım. İşte elektronikteki birinin daha önceden yaptığı bir veri seti varmış. Böyle 5 GB'lık resimler, böyle TIFF dosyaları. Onları nasıl kullanacağımı düşünüyorum. Aldım duruyorlar öyle.
Burayı anladın mı peki?
Sayılır.
Ne yani hocam?
Proje şey, radar görselleri var. Sentetik radar görselleri var. Onlar üzerinde
yoksa yarımsa?
classification yapacağım.
Şöyle ama
Deep learning kullanarak. Deep learning'in
bence hiç o zaman
böyle
proses
birkaç
yaratmadım.
deep learning metodunu birleştirmenin yolları var.
Yani 10 tane koordinat lazım.
Birkaç tane o birleştirme yollarıyla birkaç tane yine deep learning metodunu birleştirip
5 ya.
onları işte karşılaştıracağım en iyi performans verecek.
Aynen. Aynı şekilde
Çeşitli kombinasyonları mı?
Evet.
3 tane döndürüyorum. Dördüncüsü yok. Yani 5 tane eksik.
Farklı birleştirme yöntemleriyle farklı deep learning metodları.
Radar dediğin yani uçak radarı.
Uydu. Uydu görseli.
Aynen. Sadece olduğu için direkt
Evet, biraz kanser almış.
yine öncekine nazaran
Pek böyle daha önceden yapılmış bir şey. Yani
Aklıma mı?
tam olarak böyle yol gösteren bir şey yok. Daha önceden benzer şeyler yapılmış ama hepsi böyle akademik paper. Nasıl yaptıklarını
ben şey
açıklamıyor.
dosyayı yazamadım ya son gece
Sonuç gösteriyor.
Ben de işte benzer şeylere bakıyorum. Direkt sağlıklı biliyorsun genel olarak işte sahte haber tespit edeyim.
Ben şeyi hatırlayamadım bir türlü.
Bazıları çok karışık falan böyle.
Ya böyle bir kişi alıyoruz.
NLP projesi yani aslında.
Yok işte yapay zeka olacak gibi. Ben de hiçbir şey
Ben de
yapmadım.
zaten ödevden değil, sizden patladım.
Evet kesinlikle öyle.
Bakalım belki yapay zekayla olmazsa dedim NLP ile deneyeyim falan diye. Onu da olabilir.
Aynı cümleyi kullandım. Ne cevap? Bir de orada şeyler falan yok yani pointer muhabbeti yok ya. Her şey hazır.
Şey yok bir de böyle yani taglenmiş bir dataset yok. Yani öyle ya kendim bir şekilde dataset taglemem gerekecek hani zararı değil gibi.
Açıklıyorum. Şey zaten neyi var? Ya bunlar var mı?
Şey olunca pek sıcak bakmıyor şey düşündüm. Bu teyit siteleri var ya hani oradaki şeye kıyaslayacak bir NLP projesi gibi bir şey yapalım. Ama hoca pek öyle istemiyor. Bir de sınavda da öyle yapmadım ben yani.
Ha şey demiştin, 10 tane.
Daha iyi sunmuyor.
Hala
Video çektik dedi.
sayılır herhalde şey gibi.
Ya hocam müsait değil de herhalde. Bunun oldu hatta. Böyle YouTube'a video çektik dedik. Erhan Hoca altına yorum atmış. YouTube'dan.
Bir daha
Don't forget to solve it.
Haftalık toplantı yapıyor musun?
Alayım. Hafta sonu çok şey ya. Bir yandan iyi. Devamlı çalıştırıyorsun. Kaçak vakti.
Kesin böyle.
Evet, sen de son haftaya bırakıp yapmak istiyorsun.
Şeyden diyorum ben. Burada benim geçen sene ben ona erken çalıştım ilk kez. Ben de geçerim. Olumlu bir şey yani.
Ama geçen sene hoca böyle çok toplantılar falan geldi. Ya da geldiği zaman çok sorun.
Yani takıyor gibi.
Bu şekilde. Sonra ikincisini alıyorum. 4 eksi bu şekilde bunları yapıyorum. Ve en son kaç tane varsa ona göre.
Çok saçma. Nasıl yetişecek ki? Zor çünkü. Gizem. Şey sıkıntı gibi. Demo yani. Büyük öğrenci.
Şeye gerek yok.
25.000 dakika oluyor.
80 değil mi? Data structure'dan bir tanesini 180.
Şeyde herhalde işte programlama dili.
O adam bir şey bile yapar.
Kontrol bile etmiyor yani.
Hatta diğeri şey 10. Slaşın aslının olduğundan bile güçlerdi.
Şimdi diğer derslerden de bir tanıdık. Bana hiç
Benim
benim ilk yazı geldi.
o benim data structure oluyor. Dördüncü ödevi geldi bu hafta. Hatta normalde düzeyinde hoca erteledi dördüncü ödevi.
İnan mısın?
Sistemin ikinci ödevi geldi.
Çok kötü. Değil abi. Vermek zorunda.
Sen çok veriyordum.
Ben ilk aldığımda
Her hafta
ödevi,
ödev veriyor abi
ben
ya.
ilk aldığımda dördüncü şeyde midterm'de bıraktım ben. Yoksa o
Fatih
zaman
hocam veriyor.
O zaman iyiydi.
Ödevler zor olmuyor
Midterm'den
ama.
sonra da final verdi. Arada ödev
Onun da işte her hafta ödev olması stres yani.
Keşke bıraksam.
Midterm de çok kalın oldu.
Ben
Esra da
benim dediğim zaman
Benim
ısrar
var.
yoktu o derece. Ya ben ilk aldığımda
Ben olursun zaten. Hocayım ben. Fatih hocam.
Evet,
Aynı
birlikte kolluyor.
Okuyordu bence. İlk kez.
böyle şeyler
Neyse bu dönem biraz okuyayım.
Ve data structure'san geçelim data structure'dan da.
şey yapamadım.
Çalışıyor mu?
Anladım ama yapamadım.
Ben çok geç kaldım. Ben de nişan
Yok.
şeyi falan var.
Zaten uzadı.
İyi
Ben
bir
buradayım.
şeydi. Çok kaldı.
Bundan kalırsa.
Data structure bir şeyini aşardı.
Evet.
Akşam kaçta almaya gittim.
Neyi hatırlamıyorum. Bilgisayar projesinin mi? Software'ın mı? Argon'un mu? Birini yaşardım.
Şey nerede?
Algo'dan çok uzandım geçtim. Şansı geçtim. Saldım dersleri. Finalden 2 aldım sonra o geçirdi değeri.
Ya yanlış bir şey değil.
Geçen dönem mi?
2 dönem önce falan. İşte o dönem şey falan da alıyordum. Sistem programı falan.
Online mıydı?
Buraya yakın, buraya çok para veriyor. Güzel.
Sistemi nasıl geçti?
Bayağı yaptım o dönem.
Ben ilk ödevi yapamadım yani. Ne oldu biliyor musun? Bitirme projesinin sunumları falan işte data structure ödevi vardı. Son güne kaldı. Sistem ödevi.
Valla benim
Son güne yetiştiremedim. Şimdi
Şimdi
zaten az ödev veriyor. Diğer bütün ödevlerin hepsini yapmak lazım.
Sistem benim için işte operate anladığım için.
Evet.
O açıdan biraz alıyorum. Böyle şey bulmam gerekiyor da böyle. Ufak fikirler bulup bazı yerleri atlamam falan gerekiyor çünkü. Hep low level işler olduğu için.
Kafayı yedirtiyor.
Bir nokta şey yapmak. File doklamak gerekiyor. File doklayınca olmadı falan. Ben de standart output'u dokudum. Çalışıyor böyle bir şey oldu. Müthiş çalışıyor.
Ha şey yapıyor. File'a yazmaya çalışıyor ama standart output file'ı gösteriyor.
Bilmiyorum. Şu an nasıl çalışıyorum bilmiyorum. Zaten böyle initialize sıfır olarak yapıyorum ya başta. O da standart output galiba.
Aa çok iyi bir şey yazdılar ya.
Şimdi kodu sildim birden çalıştı böyle. Doklama kafasında.
Erkek kardeşim
Ondan sonra bir şey de olmadı yani. Basitten de öyle görmedim de ya. Belki de iyi demişti ya.
Yaratmış çocuk.
şansı şey yok.
Bir de şans da önemli. Bazen böyle yani ne kadar iyi yazsan da bu patlıyor falan.
Evet.
Çok anlaşılısı ya.
Geçen sene
Neden
işte
bu kadar anlaşılısı?
bir beyin fonksiyoneli sonra hoca şey yaptı. Bir zaten demo olacaktı. Midterm'de işte sonra böyle birileri sallama yapmış böyle. Tekrar alıp yaptırmışlar yani yazılmış. O yüzden yani. Sizde de böyle hoca çok şey davrandı aslında. Çok kırmak var yani. Birkaç hata falan var ama sizde de 5 puan kırayım, 10 puan. Genel olarak öyleydi yani.
İnşallah yoksa halimiz oldu.
Yani ona göre de yapmak lazım. Aşırı kötü olursa da o da acımaz yani.
Hızlı yine hikayesi.
Bir şeyde falan soruyorlar. Şunu niye böyle güzel çalışıyorsak bir şey gördüm böyle. Bu Preemptive kullanmayı falan deniyordu böyle gruplar. Bundan bir şey olmuyor galiba çok. Bazı yerlerde de kullanmamak gerekiyor çünkü bazılarla ilgili bir şey yok.
Geçen projede aynısı oldu. Async yapıyormuş. Ben de takmak gereken yerde kontrol ediyor, sonra bahsediyor. Sonra her şeyi baştan İnsan ödeve baktın mı?
Baktım şimdi. Ben ABC'de yaptığım zaman da aynı çünkü ABC'de ben anlamadım olayı. Olur. Bir eserde yaptım. Eserde yapınca bir soru düzgün çıkartmıyor. Düzgün çıkartmadığı için çalışmıyor. Her şey bitirmeyle böyle geldim.
Şimdiye kadar
Evet, buyurun. Şurada mesafeler
Okay, so we talked about the scheduling algorithms of the batch systems. Now let's talk about the scheduling. Well, I mean, all we talked about is we don't have much choice. We have to execute all of these. Should we do the first come first serve or shortest first or the shortest remaining time first? These two they don't need the preemption, but this one needs the preemption, and that's it. That's kind of the summary of the whole thing. Okay. So let's go to maybe more interesting algorithms for the interactive systems. We have lots of them, but simplest one is this one, round robin scheduling, which is the scheduler implemented by the author of your homework operating system guy. Round robin scheduling. What is round robin? Türkçesi ne round robinin? Dönme dolap. Evet, birisi seviyor, güzel. Round robin. Round robin thing is just kind of meaningless to me. It just does the same thing over and over. I don't know why do we? But I like it too. It's kind of scary too. So round robin scheduling. So it is like dönme dolap, right? Each one is a process. Only this one uses the CPU, and you keep rotating it. Okay. And this rotation, I mean, the rotation time may not depend on, it may not be regular, because I may have to wait until this process blocks, then until this process blocks, and until this process blocks, and etc. Or it could be preemptive. Or we have the prior to scheduling multiple queues, shortest process next. This will be similar to shortest job next scheduling of the batch systems. But the thing is that with the batch systems, I know how long it's going to take. That's why I know the shortest one. For the interactive systems, when you load both Word and the Excel, do you know which one is going to be terminate first? We don't, right? So that's going to be even more tougher problem. And then there will be some questions about fairness and guarantee scheduling, lottery scheduling, fair share scheduling. These are all the answers to some of our problems. And at the end, as always, we will end up with a scheduler that kind of addresses most of these problems, but there are some problems remaining. And we will say that we are going to ignore those. I mean, that's the life of the engineer. We don't solve all the problems 100%. We solve all the problems 80-85%. For the 15% of the time, we say that we solved all of them. We don't solve them. We just ignore them, right? That's it. We just ignore them. That's what we are going to do. Let's look at this round robin scheduling. This is what's going to happen. Okay, so this is my ready queue. Okay, inside my ready queue, I have these B, F, D, G, and A, and maybe first come first serve. They are put in this queue, and I handed the CPU to this process. This process ran, and now it is blocked because it asked the system to do something for it. It needs some user input and etc. It is blocked, and when it is blocked, or when it is, for example, preempted, it will be put at the end of the queue. Okay, and now F takes the CPU, and it's kind of a circular list. Okay, so you run this, then this, then this, then this, then this, and start from the beginning again. Well, you might say that, aren't we doing the same thing with the batch systems? Well, with the batch systems, usually you finish up with one of the processes, with one of the jobs, and then the next job, and the next job, and the next job. Okay? Remember the term batch, when it was initiated, it was 1950s. Okay? There was no scheduler. The scheduler is the person who loads the tapes to the computer. Okay? Context switch time in those days is the time of an operator loading the data from the tape to the computer and printing the results from computer to the printer. Okay, so these are all done by the people. So that's the context switch time. It was very, very expensive. That's why there is no context switching between the jobs. So you have to wait until the job is over. Okay, that was the batch. First batch, second batch, and third batch, we call these jobs. And this whole process is batch processing. With the interactive systems, multitasking systems, context switching is done automatically by the computer and the operating system. And this is what happens, because when B is blocked, it doesn't mean that it is terminated, it is just blocked. So we put it in a blocked list. Whenever it is ready, it will be put at the end of the ready to run list. Okay, so this is called round robin scheduling. As I said before, it could be either preemptive or non-preemptive. But as I said before, on these modern type of operating systems, whether it's the OS X, Apple's operating system, Windows or Linux or Android or iOS, doesn't matter. We do preemptive round robin, some form of preemptive round robin scheduling. Okay, so it is one of the simplest, fairest, and most widely used algorithms is round robin. Okay. Each process is timed at a time interval. It's called quantum. If it is assigned a time interval, that means what? It is a preemptive operating system, preemptive scheduler. Okay, that time interval is called quantum time. Okay, so you are given, for example, 50 milliseconds. You have 50 milliseconds, now you are running. Okay, and during that time I am allowed to run. And if I am running still, I am still running at the end of my quantum. The CPU is preempted. And it is given to another process. Of course, it is preempted means that the timer interrupt happens and the CPU realizes that my quantum time is over. Okay, so your quantum time and the timer interrupts. Timer intervals doesn't have to coincide with each other. Quantum time might be 200 milliseconds. Your timer interrupt can happen 20 milliseconds. Okay, at every 20. That means what? So 10 times while that process is running, the timer interrupt might happen. Why am I doing this? Because timer interrupts are so important. I keep timer interrupts to do stuff about virtual memory and input-output device processing and etc. That kind of stuff. So timer interrupts are not just for are not just for preemption. There are many other things that I am doing with the timer interrupts, and we will see them when we look at the chapter number 3. Okay, so if the process is still running at the end of the quantum, the CPU is preempted after the timer interrupt, of course, and another process is scheduled from the round robin queue. Okay, again, if the process has blocked or finished before the quantum has elapsed, the CPU switching is done. Good. Any questions about round robin? The thing is, here is the quantum length. Okay. Should it be okay? What is the problem? Again, I mean, I'm going to make a trade-off. Actually, I mean, we love this kind of stuff. When we don't know what we are talking about, we love this kind of discussion. We don't know the result because we don't know the optimal number, but we don't know the problem about very short amounts of quantum time. If you keep the quantum time short, what is the problem?
Context switch.
Exactly. So you learned it. Okay. So it is if your quantum time is short, okay, plus the minus is the context switch time. You are going to have lots of context switching, which is bad for the CPU memory utilization, context switching. But the plus part of the short quantum time is that for interactive processes this is good, right? Let's say I am running, let's say 10 interactive processes at the same time on this computer, okay? If I keep quantum time long, like let's say, to get away from the context switching penalties, I kept my quantum time like unrealistic 1 second. Whole second I am waiting for CPU to become available. So if I have 10 interactive processes on my computer, that means that one of the processes is going to wait 10 seconds to give an answer to the user, right? No user in the modern world of computers will wait 10 seconds. After a few seconds, I am going to hit this power button, right? So that's not good. So long quantum times are good for having less penalties for the context switching. Shorter ones are good for interactivity because I can, doesn't matter I am running 10 interactive processes, I will make sure that I am going to respond as soon as possible. So I need to do some kind of a balancing, some trade-off. Okay, so if the process has blocked, etc., I know that I am going to switch. And let's talk about this quantum length. Okay, shorter the quantum, the more responsive the system. Okay. The process switching is expensive. Context switching, again, these are the saving, reloading registers. We know that. Virtual memory maps, we don't know that much, but it is lots of stuff. Flushing the cache, it's going to kill us, right? So bookkeeping, and the worst thing is the loading of the data from the disk. Page faults. Page faults are the more expensive. Page faults. Okay. Know your enemies, okay? Page faults are your enemies. Page faults, context switching. Okay. The solution for context switching is some hardware support, for example, the multi-threading. Remember the multi-threading? Hyper-threading, the CPU say that, okay, I'm going to give you 5 sets of registers. You can switch between them very, very easily. But how about your cache? How about your page faults, etc.? For these, you need larger amounts of cache. For these, you need larger amounts of memory. That's going to make your system much more efficient. Okay, so suppose the computer quantum is 4 milliseconds and the process switch takes 1 millisecond. That means what? I am spending, okay, 5 milliseconds out of 1 millisecond out of 5 milliseconds for context switching. It is used for nothing useful actually. So 20% overhead just to stay interactive. Okay, when you feel that your computer is so lively, so responsive, that might mean that you are wasting CPU time, you are wasting your battery time. Okay, so that responsiveness is going to come to you at the cost. Okay, and if I make this 100 milliseconds, well, if I have 10 interactive processes, when I click something, I will have to wait for a second, and every time this is going to happen, I'm not going to like it. So what is a reasonable compromise? Maybe 20, 50 milliseconds. So what is my answer? I don't have an answer. I know what is bad at both sides, and we need to find a sweet spot somewhere depending on our needs, interactivity needs, battery needs, and etc. Okay? So some people say that why do we have to assign the same amount of quantum time for each process? Can we make it variable? Yeah, that might be a good idea. If the process is not a very interactive process, if nobody is using it for a while, yeah, right? Maybe I can change its quantum time. So what would you do? How would your quantum time change if the process is not interactive? Should I make it longer quantum time or the smaller quantum time? If the process is not interactive, longer quantum time or shorter? Well, if you make it longer, that means that that process is going to use lots of CPU time. So make it shorter or longer? If you make it shorter, then lots of context switching, even though the processes are not. So longer or shorter? So I mean, by just making it longer and shorter, depending on the process type, is not a good idea. We need to do something else. That's where the priority scheduling comes in. Maybe we are going to say this. Two types of processes, high priority processes and low priority processes. High priority processes are given the priority, as the name implies. So what does that mean? All of my interactive processes are high priority processes, and they are given short quantum times. Okay? So let's say I have total of 20 processes running on my computer. 10 of them are interactive and 10 of them are not interactive. So I will say that these 10, the interactive ones, are the higher priority. They are given the priority for the CPU scheduling, CPU usage. So I am kind of running two round-robin algorithms, right? For one is for the high priority, the other one is for low priority. These are my high priority jobs and these are my low priority jobs. Okay. Of course, round robin and round robin. Okay. So very short quantum time between these, long quantum time between these. I know that high priority jobs take the CPU before these. If I have an interactive job waiting to run, it's definitely going to run. But since it is preemptive, after a short while, it's going to will be suspended and will be put in the ready queue. Maybe the low priority jobs can take over after that. So keep longer quantum times for these, shorter ones for these. So here, if I am switching between them, I am getting lots of context switch time. Okay, that's a problem, but I am staying interactive. But if I don't have any of these, I will run these, and these will have longer quantum time, not much context switching, Quantum times are longer, and I am doing a fair scheduling decisions between those. That's the idea of priority scheduling, okay? So some people ask that, I mean, if I have the priority scheduling, what are the priorities? I mean, there are important users and less important users, and you might think it that way. But sometimes it is, but most of the time it is based on these kind of behavioral differences between the processes. One process is interactive, the other one is not interactive, okay? So not all processes are equally important. Assign them priority levels. Simplest version, always run the highest priority processes. Okay, well, I mean, if I let's say if 3 of them are very, very active, I'm using them all the time. Okay, if I keep running this round robin here, again, I am assuming that I have a single CPU. All of these processes will starve, right? And I don't like that, okay? So that's why pure priority scheduling is not a very good idea, not that practical. From time to time, maybe I should give some chance to these low priority jobs too. Okay? So that's what we are going to do. And the other thing is, remember one of our rules, it was the policy and enforcement. What is our policy here? Run the higher priority tasks first. That's our priority. That's our policy. But if you use that policy as a pure policy, let's look at this one. If I combine this idea with the problems of inter-process communication, that's what we have, priority inversion, right? Okay, strict priority scheduling, okay, can cause this priority inversion. I think we have given the example before. Let's look at the example again. Let's say I have three processes, process H, M, and L. The priority of H is higher than priority of M, and which is higher than priority of L, okay? So let's look at the scenario. H needs a lock currently held by L, so H blocks. L entered the critical region, okay? It holds the lock, and H started running. Since H has the higher priority, L will be preempted. H will take the CPU, but H needs that lock, okay? So H cannot continue. H says that, okay, I'm blocked. Since H is blocked, there is another process M, okay, medium level priority. It is on the priority queue, and the operating system say that, okay, it is your turn to run because H is blocked. It is waiting for something to happen, and until that thing happens, you are going to run. M keeps running, and M doesn't have to stop running because its priority is higher than L, but L is keeping the lock. So that means what? My policy of priority scheduling is subverted, right? Remember that rule. Never let anybody violate your policy rules. That's what's happening, right? So H indirectly waits for M, okay? Even though H is a higher priority, it is waiting for M because M has to run before L. So somebody smart has to say that there is a problem here. So I am going to let L run, release the lock so that H can continue running. Okay, so you might say that, well, this is a rare case, but let's look at this one. On Pathfinder, I think in 2000s, beginning of 2000s, or maybe end of 2000s, I don't know. So it was a robotic explorer sent to Mars, and after 18 months of journey, so I mean, these kind of things are okay. Since they know that it's going to take 18 months to go to Mars from Earth to Mars, most of the software development is done while the spacecraft is moving in space, okay? So 18 months is a good time to, okay, test your software and etc. So they worked on it, everything is ready, but like 2-3 days before the landing, okay, they started having this weird problem. The system keeps booting up. It just initializes, and after a while it boots up again and boots up again. In that case, nobody's going to land. The worst thing is that they are going to miss the whole planet, okay? They will be, I don't know, they will be in another orbit around the sun, etc. So it turns out that a low priority watchdog timer, okay, it comes in and it says that I am not seeing this H, so I am going to remember the reincarnation processes. They say that if this computer is healthy, if this operating system is healthy, I need to see this process, and this process, and this process, okay? So that's what was happening. One of the low priority things, it thinks that this has to be up and running. It is blocked for some reason, and it says that I am going to reset the whole system, okay? It was a priority inversion problem, and it was a bad thing, and they realized that it is happening, and they changed their scheduling algorithm. I don't remember that's what they did. So what I'm saying here is that sometimes these kind of problems it happens very rarely, but when it happens on this kind of a system, then you are in trouble. Well, you might say that, well, if we have such a problem on our computers, We are not launching anything to Mars. We are not in that critical position. No. If I have such a problem on this system and nobody notices it, maybe a smart hacker will find it, and when the time comes, okay, during the times of war or that kind of stuff, somebody may lock up all of your Windows PCs in your country, in the whole world, etc. And ransomwares and that kind of stuff, they work it that way. I think the ransomware, you know what ransomware is? What is the Turkish for ransomware? Şantaj, şantaj, fidye yazılımı. So you hack somebody's system, you say that if you pay me $10 million in Bitcoin, I'm going to release all of your data. And that's what so I think the current budget for the ransomware is much higher than all the narcotics budget of the whole world, billions of dollars. So it is much cleaner to do ransomware than doing narcotic stuff, if you are interested in that kind of thing. I'm not saying that you do it that way, but that's cleaner, right? You don't play with the human health, and that's kind of, yeah. So, but you need to find these kind of priority inversion problems somewhere to hack those kind of systems, or the simplest. What is the simplest hacking methods that you can, or the most common ones that you can find? It is Stack Overflow. Okay, it is C programming language. Okay, C doesn't check the stack, and most of the things are done in C. That's why some people don't like C at all. They might say it might be efficient and that kind of stuff, but it is causing these kind of problems. And we tell them that you are using it wrong way. Okay, so priority adjustments, again, if we have such a problem, if we follow this strict priority scheduling rules, what is the strict priority scheduling rule? Run the higher priority queue first without giving any chance to the lower priorities, is going to create these kind of problems. Okay, so you can't do that. That's against the fairness. Okay, and that will cause these kind of problems too. So what am I going to do? I am going to introduce some priority adjustment ideas. Periodically reduce the priority of the running processes. Okay, so if I use the CPU so much, that means that I'm going to lower my priority a little bit until some other low priority, I am as low as some other low priority processes. It will eventually, it falls below the priority of the next process, and they will have a chance to run and release their lock, and we will continue. Or alternatively, as an operating system, if I realize that, okay, that's what I'm doing. See, remember when I said, when the timer happens, lots of things happen. One of the things is this. When the timer happens, operating system first does a scheduling. Yeah, that's what it does. That's what the preemption. The other thing is that operating system checks whether if all the processes are getting their CPU time, and it just updates their statistics. Once the operating system realizes that these processes are not getting any CPU time, okay, I can increase their priorities, okay, or I can decrease these kind of stuff's priorities. That's what we are doing in that handling of the timer interrupts, okay. So increase the priority of running processes. That's what the operating system does during that time. It's called aging. When your process gets aged, that means that it is not using the process, okay, it is not using the CPU, then your priority is increasing. And one of the things, systematic ways of doing this is described in the slide, okay. Adjust process priority according to its recent history, okay. As an operating system, I keep a table of the recent history, who used the CPU most, okay. Let's look at this picture, okay. This will handle our, remember what I said about there were two processes. Process A is using the CPU a lot, and very short amount of time not using it, and long amount of using it, very short. This is a CPU intensive process. Process B is doing this. Very long amount of not using it. Very long amount of that. So process B is IO intensive. It's not their fault that they behave this way, okay? They have to behave this way. So in these green parts, they are not using the CPU. Maybe the fairness, there is a fairness problem between A and B. Maybe I can solve this fairness problem using the priorities. That's the idea. That's what I'm going to do, okay? Boost the priority of IO-bound processes. Why? Because IO-bound processes, they don't get to use the CPU much. How am I going to do that? I said that, okay? I said that. I am going to give you 20 milliseconds, okay, of quantum time. If you use the 20 or 25 milliseconds of your quantum time, you are fine. You are using your fair share of the CPU. That's fine. But if you use only 1 millisecond of your 25 milliseconds, okay, I am going to increase your priority by the multiple of 25. Okay, so if a process uses 1f of its last quantum, I am going to boost its priority proportional to f. Okay, it is not the fault of that process that it is using only a small fraction of its quantum time, because it has to do interaction, right? It's an interactive process. So I am going to in this case it looks like if this is one running 1 millisecond, this is running like 10 milliseconds. So I am going to boost the priority of this process B by 10, so that B has 10 times more chances of using the CPU. So with the priority scheduling, I kind of solve this problem of address the problem of fairness between the processes. Okay, fairness between the processes. Okay, so use priority classes, have separate queues for each priority level. Maybe I can do that too. Okay, one level for the interactive ones, one level for the other ones, and this is how you can determine the quantum time for each queue. Okay, priority queue. So dynamic priority adjustment, just one example here. Run queues are exactly as I said before, like this. Priority 1 is the lowest priority, priority 4 is the highest priority. These are the runnable processes. Okay, so run a round robin between them. The quantum time is smaller for this, a little bit larger, largest for this one. Maybe this one may not be even preemptive. Okay, so that's the highest priority, but the problem is there might be a starvation problem for this one or these processes. So to use the idea of aging to boost the priorities of not running processes or lower the priorities of too frequently running processes. So with these kind of changes to the priority scheduling and the priority queues, you may have a fair and efficient operating system scheduling algorithm. Good. As you see, I mean, lots of problems depending on your needs. We are all talking about interactivity here. That's why we are saying quantum time and quantum time. We didn't talk about the quantum times when we talk about the batch processing systems, right? I mean, interactivity is not there. Preemption is not important, we said that. Not much important as the interactive systems. So these are the priority scheduling stuff with the queues. Let me see if I am forgetting anything. Okay. So the thing is this, I mean, it is easy for us to talk about. I keep such a queue, and for each queue I know the quantum times, I change the quantum values. Who is going to do this? Your operating system, and the schedule is going to do that. And your operating system is getting more and more complicated, right? You are keeping all these queues, and every time a timer interrupt happens, you are checking if they are getting their fair amount of CPU. You are adjusting the quantum times and etc. And you will be very careful about not to set very stupid quantum times, like very short quantum time which like spends 50% of your time for your context switching, etc. So those are very delicate part. That's why, as end users, we don't have that much control about these scheduling stuff. It is all done by the operating system. So let's say I have, as I showed you before, as I have shown you before, let's say I have hundreds of processes running on this computer, which is happening, okay? As an operating system, if I try to keep a quantum time, a separate quantum time for each process, that's going to be too much work, okay? As an operating system, I am going to spend lots of time, CPU time, to do these kind of adjustments. Maybe I can do this, okay? For this priority queue, there is only a one single quantum time. For this one, another one. For this one, another one. Okay, that will be a better solution in terms of operating system efficiency. Operating system has to be efficient. It has to be fair. Okay, and if you try to be very, very fair, so that everything runs smoothly, that means that you are running some complicated algorithms in your scheduler. You end up using 50% of your whole computer system's resources, and that's not going to be good. Okay, let's say crime is a very serious problem in Istanbul, which is, right? Let's say to solve this problem, I hired 500,000 policemen, okay, and I have more judges and the prosecutors and etc. So it is becoming more and more fairer, more and more crime safe. But it looks like, I mean, in Istanbul there are 10 million people and 1 million policemen. Is that a good picture? No, because I have to pay them some money, right? So they end up, my police force ends up taking the biggest budget out of my economy, and that's not going to be good. I am safe, but I don't have any money. That's not going to be good. So you don't want to be in this state. So let's eliminate all the police force. Is that going to be good? No, of course not. That's going to be done in that case. Even if you have the money, you won't be able to invest that money in a safe way because there is no police force. The operating systems are the same thing too. You can't run very expensive scheduling algorithms in your operating system, okay? You have to be efficient, okay? You have to be fair, and you have to keep this balance all the time. That's why they are very difficult to design and maintain. Okay, I think we talked about this. What is my time? Okay. It is 14 or 9? Okay, 14. Okay. So varying quanta is a good idea. Okay. Many processes need just a little bit of CPU time. Okay. So don't do them too often. So since the process switches can be expensive, we don't do them too often. Okay. So both problems give lower priority queues, longer quanta. So that's what we are saying here. I think if I have, yeah, that's what I'm doing. So this one has the longer quantum time, a little bit shorter than the shortest one. Okay. Top priority is kind of a counterintuitive, right? If my priority is high, my quantum time is lower. If my priority is low, my quantum time is higher. But don't forget, higher priority jobs use more CPU time. Okay. So that's the idea of varying quantum time. They have implemented this in, okay, how do I know that which process is interactive and which process is not interactive? Okay, during the times of, okay, there is a mainframe, which is a large room size computer, and these are all connected to the terminals all over the university campus. Let's say I have hundreds of terminals connected, and they are connected to this computer, and there is one CPU. These are dumb terminals. There is just a screen and a keyboard. That's it. Okay. So each one is, of course, I am using time sharing and multitasking operating system. Each one is trying to do something. Some of them are interactive. For example, some of them are typing their word processing. They are using their word processing application. The others are doing some scientific computation. That means what? Word processing tasks should have higher priority because they are interactive. The other ones, they should not be that high priority because they are not interactive. Of course, I have to be fair too. So somebody smart implemented this. They said that if there is a person here, okay, doing this interaction, he or she must be clicking on the keyboard most of the time, right? Because they are doing interaction. If this person is just looking at the screen and doing nothing, not interaction, waiting for the results to happen, it is not interacting with the keyboard. Okay, so this means that this is not an interactive job. This is an interactive job. Let's boost the priority of this job. Okay, good idea. But then somebody realized that even though if I am not running an interactive job, if I sit in front of the computer and regularly hit the enter button, okay, so the computer operating system thinks that my process is an interactive process, is going to increase my priority and my job will run faster. They did that and everybody realized it, and hundreds of people are just sitting in front of their terminals and they are hitting the enter button all the time so that the computer thinks that their priorities are high. So I end up having lots of high priority jobs. I end up having smaller quantum time and high priority jobs, and I end up having lots of context switching time. So at the end, I will have a very, very inefficient computer system. That's what happened with this CTSS computer in 1970s. So now, but nowadays computers, we don't have that such problems because, I mean, interactivity is something different compared to those days because we have the mouse and we have the touch screens and etc. Okay, I think I am going to stop at this point. If you have a question, I can take it. Yes?
Where do you keep those kinds of information?
Where do I keep?
These kinds of information, I mean the time for frequency of the process.
Of course, in your process table.
Process table.
Yeah, process table is something complicated. Okay? That's why it is in the kernel. And every time a timer interrupt happens, the operating system updates all those kind of statistics in the process table. Who used what? How many seconds they use the CPU? What kind of memory accesses they have? How many page faults they have caused? These kind of statistics are kept in the process table or the thread table. Okay? Yes?
Can you explain again? The mean time I think turnaround. Some property 4A plus 3B plus 2C plus D.
You are talking about the batch operating system? Yeah, batch operating system, yes. Well, in that case, you mean the shortest, what is the reason for the shortest job first?
It was the longest job first. A was 8 minutes.
That's the bad for the throughput time, right? That's the bad case, not the shortest time is good for the. Let's go to which one is that? Yeah, here it is. Yeah. We say that if you do the shortest time algorithm, it is good for the turnaround time. What is the turnaround time? You calculate the running time of each process and divide it by 4, right? So if I run the longest one first, everybody has to wait for this one to be finished, right? So I have to add the runtime of A to this one, and this one.
Okay.
But if I do the other way, I have to add the shortest one's running time to each of them. That's why this one says that to keep the turnaround time lower, run the shortest one first. Okay. Obviously, the total amount of time is going to be the same. I am trying to improve the turnaround time. Okay? Okay, and then I will see you tomorrow morning.